Okay, um, good morning, everyone, and welcome to the GISS Sea Level Rise seminar. Today, we have Dr. Derrick Lampkin. He's a member of the research faculty at the Department of Atmospheric, Oceanic, and Earth Sciences at George Mason University and the Senior Research Program Scientist at NASA headquarters. He's an expert in studying glaciological processes using remote sensing observations, numerical modeling, and field observations, and has performed extensive research into ice sheet surface hydrological processes and ice dynamics. Prior to his current position, Dr. Lampkin served as an assistant professor and research scientist at University of Maryland and Penn State University. And he earned his PhD in geography from the University of Arizona and a master's in geography and BS in geological sciences from Ohio State University, where he conducted research at the Bird Polar Research Center. So we're very glad to have Dr. Lampkin. Today he will be speaking on the topic Greenland's shear margins in a warming climate, a summary of work over the last decade.
Okay. Hi, thank you, Patrick, and thank you all for, thank you, Patrick, for the wonderful introduction, and thank you all for your time and attention. Also see some old friends on the list. Hi, Richard, and hi, Ken. Hope you guys are well. Most of the work here is a lot of work that probably poor Richard's heard before. Actually, the inception of this work really started while I was a faculty member of the Pennsylvania Ice and Climate Group. So Rich Alley had a lot of input in the early development of some of the work that we did. Let me pull up and share the presentation. So the work entitled Greenland Shear Margins in a Warming Climate, a summary of work over the last decade, is really a summary of the kind of work that we did in the early examination of surface hydrologic features on the surface of the Greenland ice sheet, which at the time didn't receive a lot of attention. In large part during that period, the impact of superglacial lakes, the elucidation of the understanding of how the superglacial system evolved and in what ways it was, in what capacity it had for delivering copious amounts of surface melt into the inglacial and subglacial system was a paramount focus at that time. So people were really looking at big superglacial lakes at the time. During that period, I was also looking at superglacial lakes, superglacial channels. I had students that were mapping superglacial channels and their relationship to lakes. And we started to notice that in the Jakobshavn region, water-filled crevasses along the flanks within the shear margins of Jakobshavn. Of course, Jakobshavn is a well-known marine terminating outlet glacier with significant capacity for delivering a solid mass discharge into the ocean from the Greenland ice sheet, and has been an important component of the overall understanding of the contribution of Greenland mass loss to the ocean. And so we started to notice these water-filled crevasses and started to ask questions about whether or not they were significant, how they changed over time. Did they contain the same volumes of water that we saw in superglacial lakes? And more importantly, what kind of impact would you get if you squeezed surface meltwater into a shear margin, especially for a fast-flowing outlet glacier like Jakobshavn with its significant dynamics? So that began this work. And that's a long time since this picture, back when I used to have hair. That's me behind the late Ian Willens. when I was doing work for him in West Antarctica as an undergrad at the Byrd Polar Research Center. And so where we've come today, in large part, is that we know that Antarctica and Greenland are experiencing negative net mass balance, with Greenland demonstrating a large proportion of that mass loss between the two ice sheets, which we're all familiar with. And, I guess the prevailing understanding is that a large proportion of the mass loss out of the Greenland ice sheet is proportioned into about 60-40, about 60% runoff and 40% solid mass discharge through marine terminating outlet glaciers such as Jakobshavn. If you look at this profile, which is a classic profile that has oftentimes been shown in many of the presentations in our community, we're all examining different aspects of these marine terminating outlet glacial systems along this profile. And my particular focus has been here in the upstream part of these outlet glacial systems, where superglacial hydrology, lakes, and channels predominate. But these water-filled crevasses are really quite interesting systems. We find that not only are they in shear margins, but they're also near the calving fronts. So water-filled crevasses can play a significant role, not just in upstream dynamics, shear margin dynamics, but also in the calving process as well. And not just for marine terminating outlet glaciers, but also for ice shelf processes in places where large tabular ice shelves play a significant role in regulating mass balance components in Antarctica. We largely, in examining these water-filled crevasse systems in the Jakobshavn outlet glacier system, posed these three kind of major research questions. One, what is the spatial distribution and drainage behavior of meltwater in the shear margins? What impact does drainage from shear margin ponds have on regional ice flow and mass flux? And what is the relative contribution of shear margin lubrication and calving have on extra marginal ice flow? So we're not just interested in what these water-filled crevasse systems can do to the ice stream proper, but what impact can they have on regulating or influencing mass flux into and through the shear margin system, and primarily into the region of fast flow for the outlet glacier system. This culminates, these questions were divided up into a sequence of papers between 2013 and 2018. Largely. And so you can see here kind of a general summary. In our 2013 paper, we were asking questions like, what were these structures? No one had really spent a lot of time examining these shear ponds. And so we wanted to find out, like, why are they there and how do they vary? What is the spatial and temporal variability of these ponds? And more importantly, how much water do they contain? Later on, we started to ask the question, what is the interseasonal variability of these marginal ponds? And what are their drainage behaviors? And more specifically, what are the kinds of ways in which we could bound what the potential impact of drainage from these features are, if we assume that meltwater from these features were to infiltrate to the bed and lubricate the shear margin. We continued on in further papers to ask, what is the long-term variability in the hydrologic state of these shear margin ponds? And there's a specific reason why we focused on hydrologic states at the time and not volume or estimations of volume, which was not easy given the limitations of the data sets that we had available longitudinally. We went on to ask, how has pond area changed over time? What are the upper bound effects of drainage and impact on regional ice flow? Whoops. And what are the overall impacts what is the overall significance that we think subglacial hydrology can have in these shear margins as meltwater is injected into them? Presumably, what we'd expect is that in a warmer climate, increases in surface melt can proliferate greater volumes of and production of surface meltwater. these shear ponds offer additional opportunities outside of the other mechanisms that we understand are important in the drainage of superglacial lakes to get water into the interior of the ice sheet and influence Greenland's evolutionary capacity for moving mass to the ocean. So I'll walk through an introduction of these systems. I will highlight and walk you through results that give us an understanding of initial observation of these systems with a focus on the Jakobshavn-Isbrae system. We delineate over a single melt season for this particular work. We map the areal extent and variability, and we characterize the glaciological setting in which these shear ponds were found. We also evaluate the properties and behavior of these systems in respect to topography, local strain rates, and et cetera. And we come up with a bounded estimate of what we think the drain volume is from one of the largest water-filled crevasse systems. At the time, we were calling these saturated crevasses. You know, I'm not even sure what is a really appropriate nomenclature for these. And the reason why is because they actually occupy a spectrum in terms of their hydrologic morphology. Some of them look distinctively like water-filled crevasses, distinctive individual crevasse systems that are isolated from each other and water-filled. Others were effectively water-filled ponds or shear saturated ponds. So you had something that looked more similar to the superglacial lakes that we see in these extramarginal fields. So, you know, the nomenclature probably over time might change in regard to our expanded understanding in classifying the various morphologies that these water-filled crevasses or saturated crevasses or ponds or shear ponds or fracture ponds occupy as work has examined these features over other outlet glacier systems beyond Jakobshavn, which has happened over the last few years since I've been doing this work. What we found for these particular ponded systems, and actually let me go back here. In this image, you're seeing Jakobshavn, and we delineated 7 major distinct pond structures, which we characterize as CV1 or designated as CV1 to CV7. You can see that they range along both the northern and southern shear margin flanks of Jakobshavn. Some are really well within the area of fast flow, and some are separated shear margin water-filled crevasses, and then some look more like cohesive ponds. We found that the saturated crevasse regions are associated with depressions in surface elevation along the shear margins that are correlated with depressions in the basal topography, which should not be a surprise. And this is true overall for most of these saturated crevasse systems. Now, what's really quite interesting is that there is a variation in the ice thickness along the length of this section of Jakobshavn that was occupied by these water crevasse systems. So obviously that might have an impact on the infiltration capacity and also the transfer of basal roughness that can influence the magnitude of depression depths in the surface topography. And so we think that the higher elevation saturated crevasse systems tend to look more like separated, individualized crevasses because the magnitudes of undulations in the surface topography are a lot more subtle than what you have downstream, where the ice thickness is not as high. During this particular melt season, we examined the cumulative area of each of these saturated crevasse systems. So the top panel shows you with the bar graphs what the accumulated amounts are, and it's separated out by each of the individual saturated crevasse systems. And we were interested in evaluating how this aerial extent changed with changes in interseasonal temperatures. And obviously what you can expect is that as the season got warmer, the aerial extent of these saturated crevasse systems expanded. Now you might ask, like, well, what does that really look like if these pond systems varied in terms of their morphology? What we saw for the more cohesive saturated pond systems is that they expanded their area and still remained largely cohesive in the same way that you would expect with extramarginal superglacial lakes. With the upstream individualized or separated water-filled crevasse fractures, the fracture network just expanded. Some integration or combinations of these fracture ponds occurred as the temperatures warmed. But what we just generally saw was an expansion in the total area across which these systems occupied, even though they still remained distinctive and individualized at higher elevations. In the bottom graph, you can see the change in area more distinctively for each of these crevasse systems. Our CV1, 4, 5, and 6 became inundated sometime between June 6th and June 22nd. And we'll have a chance later on to look more at how these systems change over longer periods of time. During this particular season, we were interested in what the crevasse filling and drainage rates were for these particular systems. We defined our crevasse filling rate as the change in area between the first image date, which was June 6th, and the maximum or peak area achieved during the analysis period. Of course, using optical imagery in order to characterize features as this, where we suffer, like many of us who are using optical data to examine superglacial features across these ice sheet systems, by the limited availability that cuts down the frequency of sampling as a result of significant cloud cover. That's always a problem working with these data sets, and this is something that we suffered from as well. It turns out that in this particular season in which we'd examined these systems, we had reasonably decent amount of clear sky days, and so we were able to readily characterize the properties of these crevasse systems. Overall, the filling rates increased with elevation across most saturated crevasse systems. The lower elevation systems experienced higher melt rates and greater runoff, which we think was likely connected to well-developed inglacial plumbing through moulins and crevasse fields. Overall, this is during a period in which earlier work by Colgan 2011 showed that crevasse area extent and density has increased by 13% over a 24-year period from 1985 to 2009. So that's a broader contextual picture on the fact that crevasses in general have become increasing feature dominating the ablation zone. And this is particularly true for these crevasse systems along the shear margins of Jakobshavn. We derived using our optical imagery estimates of our strain rates, and we tried to evaluate the relationship between strain rates and the drainage behavior of these water-filled crevasse systems. The drainage rate was calculated as the difference in area at peak extent and the area measured on the last image date for which the crevasse group was mapped. So you can see what the change in area as a function of the drainage rate is on the left. It tends to be roughly linear for each of these saturated crevasse groups, even though they're not linear as a function of elevation. And then on the right is the relationship between our estimated strain rates and the drainage rate. And that's a bit murkier. You can see that there isn't a clear-cut relationship. This could be a result of the limitations in the data sets that we used, but it also could elucidate more complex dynamics that are driving the drainage behavior of these features. And this will become a little bit more relevant as we move along and look at how these drainage behaviors varied over longer periods of time. Ultimately, in this particular season, we were interested in just coming up with a bounded estimate of how much water drains from these features. So we focused on the CV2 system, in large part because it was the largest, it was the most spatially cohesive, and we assumed that big area means lots of water, ideally. So we looked at the aerial change between CV2 between July 8th and July 24th. We used we primarily used a couple of methods for estimating depth, which was the most difficult aspect to extract an estimate for volume once we knew the change in area. The one that's probably the most useful is this modified Knight approximation, which estimates the balance between longitudinal tensile strain and creep closure due to ice overburden pressure, which gives us a direct estimate of a idealized fracture depth. So using that information within the aerial extent of the mapped CV2 saturated crevasse pond, we were able to come up with a bound estimate for what the potential drainage volume was for that time period. And it was roughly 0.0249 cubic kilometers over that period. That is comparatively a magnitude of water that's almost consistent with smaller superglacial, traditional superglacial lakes in the extramarginal field. So with that, we started to consider that, at least for the larger ponds, we're in the range in which we're looking at volumes of water that we know are consistently significant in influencing ice behavior and ice flow behavior during the summer for superglacial lakes. Now, this may not necessarily be true for all of these saturated crevasse ponds, since the magnitude of volume of water probably varies across these systems. The larger ones may be more significant in influencing more directly, localized ice dynamics, whereas the ones that are smaller, more distributed, may not have as significant influence. And I'll talk a little bit more about what are implications there for how these systems may or may not be impactful. We also were interested in further work in characterizing the spatial and temporal variability of these systems. So we assessed the long-term variability and hydrologic properties of these systems, analyzed changes in the aerial extent at the decadal timescale, and evaluated the drain state of these systems over time. Using Landsat ETM Plus panchromatic data from 2002 to 2013 for as many cloud-free scenes as we can get, you can see what the frequency of days are that were assessed by month for May, June, July, August, and September during the melt season from over this time frame from 2002 to 2013. You can see that most of our scenes actually occurred during the period of peak temperatures as measured from surface meteorological stations. That's actually pretty good. We really wanted to be able to get scenes that were, sorry about that. I think I'm back now.
Yes.
Okay. I don't even know where I lost you guys, so I'll go back a little bit. Let me reshare the screen here. And
the last step I remember was water depths were similar to the areas outside the margins that had influenced ice flow before.
Excellent. Thank you very much. Let me see. Maybe I'll just start here. Let me share the screen. Thanks for your patience. Sorry for the technical problems. So in large part, what we really were interested in is using a multi-center data fusion approach to try to characterize what the drain and drainage rate and fill states were for these saturated or water-filled crevasse systems. the Heisenbergian trade-off here was that using automated routines to apply to optical data to delineate the extent of these features from multiple data sets was a Herculean task for one, and two, there are complications in the performance of automated routines over heavily crevassed systems, in large part if you consider the influence of image acquisition geometry, which results in shading and shadowing. The accurate delineation of these features is severely complicated with the application of automated routines. In the previous work for the saturated crevasse systems that we delineated for one season, we did by hand. So it would have just been untenable to be able to do that using Landsat 7 and 8 data, Google Earth historical imagery, PGC imagery, EO1, ALI, SPOT, and ASTER data, in which we leveraged between the 2000 and 2015 season. In this graphic, what you can see, let me open this up here, is the field occurrence of these saturated water crevasse systems over May, June, July, August, and September during this time frame. Apparently, what's clear is that the field states are peak during the peak period of summertime temperatures, are correlated with the peak period of summertime temperatures in July. Even though over time we're seeing that this peak has actually been shifting in the ablation zone to later and later in the melt season. But this analysis was just done up until 2015. This is consistent with what we saw in the 2007 season, in which we initiated our initial analysis. You can also see that this temporal assessment of field states, we extended back a bit more to 1999. So you can see in graphic A along the y-axis the number of field days on the left side. On the right side, these are blocked by each of the saturated crevasse systems. And you can see that we've got up to 30 days, or about a month roughly, for each of these saturated crevasse systems. Some seasons, these total numbers were lower, some were higher. We attempted to try to characterize patterns, temporal patterns in these. So we kind of delineated 5 major periods that we thought were distinctive from each other over this time frame. But the take-home message is that the cumulative monthly days of field states were significant throughout each of these melt seasons, with some seasons with much lower occurrences for certain saturated crevasse groups. By and large, largely the higher elevation saturated crevasse groups kind of had fewer number of field days than the lower elevation ones. And the really interesting thing that we noticed, it was probably the most significant observation from this, was that we examined multiple drainage events in one season. For example, CV1 drained 5 times in 2011, which means that the water field crevasse system filled up, drained, filled up, drained, and filled up, drained at least 5 times during that one season. What that meant was that somehow these systems are being fed with significant amounts of surface melt water, multiple throughout the melt season, and conditions are such that these features are able to drain. So what we're looking at is the capacity for these superglacial shear pond systems to inject meltwater multiple times in a single season. This is also part of that decadal analysis. And so this is a little bit complicated graph, but effectively what you're looking at are drainage rates by the individual bars, gray bars. Each row is a saturated crevasse time series. The variability in estimated surface temperatures are evaluated in the lower graph by the red dots superimposed on the CV1 drainage time series. And then we also estimated strain rates as well for the data that we had available, but the timeframes were limited. Those are depicted by the black dots that are connected, and the right-hand side scales are associated with those. By and large, you can see that we've got some differences in kind of pre-2006, 2008, and then post-2006, 2008, where we see much greater variability across all of these saturated crevasse features. That's kind of correlated with increases in temperatures after 2006, which were increases as high as 2 degrees C. And we see an increase in multiple drainage events across these saturated crevasse systems as we moved into warmer time periods, which kind of makes sense. Now we started to ask questions about implications of what happens when you inject meltwater into a dynamic shear margin system like Jakobshavn. So we wanted to evaluate the potential impacts on mass flux through marine terminating outlet glaciers, in particular Jakobshavn. And effectively what we had postulated is that an increase in lubrication of the basal environment within the shear margins could potentially enhance ice discharge from upstream and influence or increase the amount of ice flow into the main trunk of Jakobshavn. And so here we've got kind of a generalized representation of what we hypothesize how a process like this could occur. We get drainage at the shear margin region where a water-filled crevasse is. So in the lower left graphic, you can see step 1, drainage. This is if you were examining a cross section along a flow line that is tracking from the shear margin out into the extramarginal field. We get lubrication at the bed if we assume that water infiltrates directly to the bed. We get enhanced ice discharge as a result of basal lubrication. That mass displacement accentuates upstream longitudinal stresses, which propagates the influence of that perturbation, mass perturbation, flux perturbation in the shear margins farther into the extramarginal field, which also increases ice flow and mass discharge farther out away from the shear margins. So we set out being able to try to create a model that would bound this problem in such a way to test this hypothesis. So we utilized ISSM and developed a plane model with all of the usual accoutrements in such a diagnostic model by deploying our conservation of linear momentum, where assuming acceleration is negligible and ignoring Coriolis effects. Ice is treated as a viscous incompressible fluid, and viscosity is obviously modeled using our well-known Glenn flow law. Our model setup initially was a steady state model using the Selfie-Streamy ice flow model, which assumes vertical shearing is negligible and reduced strain tensor to a system of 2 systems of equations and unknowns. We prescribe boundaries with surface and basal topography, geothermal heat flux, surface mass balance for surface forcing, which we assume is 0 in order to constrain what the dynamic effects are from drainage of these shear ponds, and then utilization of surface velocity data. More specifically, we use a Coulomb-style basal friction law by assuming that within the cumulative drainage or drainage extent or inundation extent of these saturated crevasses, that we have a thin water layer that forms at the bedrock ice interface within the shear margins under the assumption that water from all of these pond systems are able to infiltrate directly to the bed. And then we're examining the ice velocities along these flow lines, flow line 1, 2, 3, and 4, which vary upstream from the terminus of Jakobshavn. And our steady state perturbation model shows that ice flow amplified within 10 kilometers of the ice stream, 10 kilometers away from the margin in the extra marginal field, by as much as 20%, resulting in an increase of about 0.6 gigatons a year in ice mass flux, enhanced ice mass flux into the ice stream. That's largely for the southern ice margin. The northern ice margin is a little bit more complicated, in large part because the outboard ice is largely carried along the parallel to the prevailing direction of ice flow in the main trunk. And then there's a limited section downstream where ice is entrained into the main trunk. That's different than the southern margin, where ice is entrained into the main trunk at multiple points along the length of the shear margin. This also corresponds with acceleration within the ice stream on the average of 4%, and in some cases, in locations, it was up as high as 12%. Here you can see in graphic B what the change in velocity is from the non-lubrication to lubrication state as a function of distance away from the shear margin as well. And the lower table just gives you what the values were that we estimated mass flux through the shear margins as a function of enhanced lubrication due to potential infiltration by these shear ponds. We ran a transient perturbation model as well. We ran a model at 2-week intervals from 2017 to 2027. And we were just examining as a sensitivity analysis what were the enhancements that were associated with the degree in which that amount of ponded water lubricated the bed over different periods. So we looked at consistent lubrication periods over 60 days and 90 days. This is in large part because we didn't have well-constrained information about what the basal drainage capacity is in the subglacial system. We don't quite have an understanding about what the configuration of the subglacial hydrologic system looks like, let alone when water is injected over short periods of time into the shear margin system. What we do know from previous work where basal water pressures had been measured is that they're really quite high, to the point where about 99% of the glacial static pressure is compensated by the bedrock water ice interface hydrologic pressure. So we ran a sensitivity analysis, which is represented in graphic C at the bottom, where the proportion of the glacial static pressure that is compensated by the thin water hydrostatic pressure was set to 99%, consistent with field measurements, and then at lower amounts in order to gauge these other modalities or conditions in which the proportion of compensation is less. And in all of these cases, the middle graphic, is the one where we evaluated changes in velocity along these flow lines on average as a function of changes in the areal extent and hence the lubrication zone, basal lubrication zone. And we scaled the change in area with estimated changes in temperature. So that's why you see that variation. And clearly, the larger these things get, the more area they inundate, the larger the area in the basal environment that they lubricate, the greater the impact on ice flow and mass discharge. We also was interested in seeing if we can see in any given sets of seasons the effect on ice velocities corresponding to drainage events or observed drainage events of these features. So we used Landsat 8 OLI data, velocity products derived from Landsat OLI, and tracked changes in surface velocities along our 4 flow lines between May 2013 and August 2015. The speeds were computed using a feature tracking method with varying 16-day samples intervals. Those intervals varied between 16 and 96 days. And this data was provided to us by Twyla Moon and Mark Fonstock. You can see along the flow line data in each of these four graphics, speed in meters per day on the y-axis on the left, year along the bottom, and then distance away from the shear margin. And so basically you can see that our speeds are highest near the shear margins where the red colors are, and then they exponentially decrease as you move farther away from the margin. We tried to relate this, these profile increases or profile velocity profiles or velocity change profiles with the observed drainage events. So this is an example of the drainage events that we characterized for 2014. In the top graphic, you can see the saturated crevasse numbers 1 through 7, the same ones that we've been examining in previous work. And the blocks indicate the periods over which we've observed the presence of them being filled. So we assume that after the end of the block, that's the date at which that water-filled crevasse system drained. So this gives us an estimate of the period across which we could have drainage occurring. We have a sequence of drainage events that are characterized by a number of blocks for CV 1 through 4 and 6 and 7 that drained. And then we have multiple drainage events for CV4 and CV3 and CV2. The average velocities of the entire flow line for each time period is compared with the average velocity for the entire melt season from May 31st to September 30th. So that's what you're seeing in the middle block. It's not so clear here, but ideally what we were looking for were spikes there that could potentially be associated with the observed drainage events from the saturated crevasse systems. That's a little bit true for a spike that might, for across these flow lines that correspond to the period where we had the largest integrated drainages over those saturated crevasse systems from 1 through 4 and 6 and 7. And then the lower graph just shows you the profile view that's representative of the same kind of data that we saw in the previous graphic on the last slide, which is this exponential decay along the flow lines. What's clear though is that we have a % increase in max summer velocities that are relatively and observably high close to the shear margins, and they exponentially decrease as you get farther away. So we started asking ourselves further questions. Can we decode what's happening in the extramarginal field? So we evaluated velocity changes on a weekly time scale to examine ice accelerations in the extramarginal field. We also started to ask the questions of how much of these extramarginal field ice velocities and observed changes related to calving events at the front, shear pond drainage from our saturated crevasse system versus far field superglacial lake drainages. And of course, this gives us some implications for scale response to oceanic forcing in terms of the extramarginal ice field. So if you look at our same flow lines that we used in previous studies, our cumulative saturated crevasse extents that we evaluated previously, we've extended our domain a bit out farther into the extramarginal field, which gets us out, in the 25 kilometer range away from the southern shear margin. We have an assemblage of superglacial lakes. They're numbered here 1, 2, 3, 4, 5, and 6. 6 being the largest and farthest away along flow line between flow lines 1 and 2. And so we were just starting to ask the question, how much of any of the observed extramarginal field accelerations were potentially due uniquely to drainage in the shear margins relative to drainage from far-field superglacial lakes or to upstream dynamic response to calving events at the front. And so this was just unpublished work that I started that I actually haven't finished. There's a complicated set of moving factors here in this graphic, but in graphic A, what you're looking at are weekly timescale changes in velocity anomalies along the profiles. So on the y-axis, you're seeing the time and day. So it's from June 3rd all the way up to September 19th, 2017. At the bottom, you're seeing the elevation profile along that flow line. So you can see where the margin is, the direction of ice flow along that flow line, and an evaluation of where the bed elevation and surface elevation are, which gives you an idea of what the thickness and bed elevation topographies are. And then what you're looking at here with all of the really cool colors are the velocity deviations at each location and these 100-meter increments away from the calving front, or sorry, the shear margin front. And so what we're seeing is that we have smaller magnitudes, well, higher magnitudes of positive increases in velocity anomalies near the shear margin. That decreases a bit as you move farther out, roughly at about 8 kilometers. And then beyond that, we see very large increases in flow velocities in the deep extramarginal field at 10 to 13 kilometers away from the shear margin. In panel B, which you're looking at over the same time frame, are the retreat in advance of the calving front. And so the red marks, or the red bars, indicate calving events where we've got retreats associated with observed breaking off of ice into the fjord. And then panels C and D show the far field superglacial lakes that I mentioned, L1, Lake 1 through Lake 6. And so you can see over the same time period that we're evaluating the changes in velocity, what the drainage behaviors were of those lakes. I think at the top there, you can see for each one of those bars, I think these might have been the aerial extent, max aerial extent for each one of those lakes. And then in the last graphic D, you can see our standard saturated crevasse systems, CV1 through CV7. And then you can see what the drainage states were along that time period. Of course, we've got observed multiple drainage events in this 2017 season as well, which is really cool. What we show here is that the extramarginal velocities from our 16-day Sentinel data for 2017 from June to September shows that velocity anomalies are not correlated much with changes in the calving front. The far field anomalies might be forced by large superglacial lake drainages, which we try to substantiate by using a diagnostic model, employing ISSM again. We're utilizing running the basal subglacial hydrologic kinetic transient interactions model, SHACTI, which evolves the subglacial hydrologic system by implementing a conservation of mass, evolution of network geometry, and basal water flux, accounting for internal conduit melt and closure. We have an idealized superglacial lake drainage event where we assume a vertical conduit that is directly delivering water to the bed. So we run SHACTI in phase 1 to produce an estimate of subglacial effective pressure. Then in phase 2, we run a diagnostic ice flow baseline model for the no water case and the no drainage case. And then in phase 3, we run the same diagnostic ice flow model with a lake drainage water case with transient meltwater injection to the base over a 10-day period. Assuming that we've got a subglacial evolutionary network that's a linked cavity to our channel conduit system. And so our preliminary results show that you can see what the increase in velocity anomalies are along flow line 1. So flow line 1 in the upper part of the graph is buttressed right up against the shear margin. You can see where the ice flow direction is. And for this single idealized lake within the regions of the assemblages of observed lakes, this is where our lake drain center is. And so you can see what the velocity anomalies are that are associated spatially with drainage to the bed from our idealized lake, which could elucidate the fact that in the farther edge or upstream edge of our flow line, those increases in velocities could be associated with these effects of lake drainages. So yeah, here we have percent difference in velocity associated with no water and water cases. So ultimately, we can ask the question, what controls the magnitude of response in the shear margins when we inject meltwater into the bed? What are the things we don't quite understand? And what are the implications for other major outlet glaciers that are increasingly dominated with surface meltwater features such as these water-filled crevasses? The one thing we have to consider is what's happening at the bed. Whoops. And obviously, this is where the rubber meets the road. The configuration of the basal hydrology controls the entire ice dynamic response to the infiltration of meltwater injection. For our 7 saturated crevasse systems, what you can see here is that we've got relatively low basal hydrologic gradients for saturated crevasses 3, 6, and 7, and higher gradients for 1, 2, and 4. Those basal gradients actually have an influence on how the subglacial hydrologic network responds and the degree in which these subglacial or basal systems remain pressurized. For not well-formed basal hydrologic systems, the pressurization is higher, and hence the capacity for the glacial static pressure to be compensated for is much higher. As water is injected into these systems over and over, that capacity is decreased. Now, this is I think, a much more complicated set of systems to deal with than the considerations that we have for considering how the basal hydrology evolves for standard extramarginal drainage from standard superglacial lakes, in large part because of the conditions within the shear margins. We have dynamic conditions, we have substantial compressive and changes in compressive and tensile stresses, strains that can influence the overall temporal evolution of these subglacial hydrologic systems. So I think it's worth more work to try to understand what is the relationship between how meltwater, injected meltwater from the surface influences the initiation of evolution in the subglacial hydrologic system in these marginal environments, and then how that changes as a function of feedback from the surface that may influence regional strains that could induce further drainage. So in conclusion, we integrated over all of this work. We presume that for the Jakobshavn system, there's enough water in some of these saturated crevasse systems to influence changes in the mass flux. We are considering that the primary impact that these systems, drainage from these systems could have is on the on weakening of the shear margins through basal lubrication. What we hadn't accounted for is the possibility that cryohydrologic warming could be a potential for saturated crevasse systems at higher elevations where the ice thicknesses are larger, and the capacity for entraining that infiltrated drainage from the surface meltwater directly to the bed may not be be forthcoming. So it's possible that those more distributed assemblages of separated higher elevation CV2 systems like 6 and 7 may not deliver water directly to the bed, but deliver water into the inglacial system where it can refreeze and overall influence and weaken the shear margin due to cryohydrologic warming. We've established that enhanced extramarginal ice acceleration can occur between 7 and 10% and could be under certain circumstances as high as 30% assuming under the best case that all of the water and all of these saturated crevasse systems are draining to the bed and lubricating the bed, in equal fashion. That's likely not the case. The magnitude of impact of drainage from these systems decreases with distance from the margin, and the magnitude of impact depends on the basic hydrologic configuration. Overall, I think this brings up some interesting issues, like how does changes in margin conditions influence transmission of stress perturbation from the terminus, and how is that modulated by drainage from these water crevasse features? Do they act to enhance or retard the transmission of stresses due to terminal conditions at the front? What are the impacts of interactions among calving perturbation, shear pond drainage, far-field lakes, and how do they overall affect the observations and changes in velocities in the extramarginal field? And lastly, what I think is really an interesting result of this work, which wasn't intended, is over what spatial and temporal timeframes do these interactions result in observed coupling between far-field ice acceleration and oceanic-induced calving, since our prevailing understanding about these outlet glacial systems is that changes in the calving front or perturbations in the calving front are largely responsible for the changes in observed mass flux far away from the calving front, deep into the upstream ice flow field for these outlet glacial systems. What I would propose is that there seems to be a substantial decoupling in the ice response over weekly timescales, but over obviously longer timescales, diffusive dynamic factors propagate these terminal events deeper into the extramarginal field. The question is, to what degree do drainage from these features, the alteration in the force balance of the fast flow outlet glacier like Jakobshavn, by virtue of lubricating the shear margins, influences or enhances what the terminal effects are? And with that, I'll stop and take questions.
Okay, thanks very much, Derrick. See, we have a question in the chat from Vivian. Let's see. She asks, does saturated crevasse melting along shear zones supply more basal meltwater than saturated crevasses within the ice stream? And how do you recognize when saturated crevasse drains? Is it visible on the satellite imagery?
Thanks for the question. Most of these pond assemblages they range a distance from within the shear margin. Obviously, the shear margins is not like one location, but it's a zone. We see that in the middle of the Jakobshavn region of where fast flow is most prevalent. We have limited number of these shear pond systems, even though over time, the more recent data I've looked at shows that these pond systems are getting larger at higher elevations. And we're seeing really strange things like interconnectedness of these systems by interstreams that are cutting across the middle of the ice stream in the higher elevation zone of Jakobshavn. So I think we're seeing an evolving configuration in the morphology of these systems as these as environmental conditions continue to warm, and also as the ice front continues to recede. The ice front today is not actually where it used to be when we started this analysis. So CV1 is gone at this point. And the second question was, how do we delineate them? Painstakingly by eye. It's horrible. It's horrible work.
I think she's also asking, how can you tell when the crevasse drains?
What we can't really account for, and that was a tricky one, is the circumstance of partial drainage. which we actually had in some cases. But basically, what we're looking at is the change in the areal extent to characterize a drainage event.
Are there any other questions?
See, one is from Jeff. Where's my chat? Let me see the chat. Let me open it up. Thanks, Derrick. I have done many things. Melt along shimmers, find more base of water, etc. Okay. Can one determine the change in the plume at the ice front? So we didn't examine. We only examined the saturated crevasse system, so we didn't look at any potential influence on meltwater transport into the fjord beyond the calving front. So it's a good question. I don't know if I spent time actually looking for whether or not we could observe plumes. Oftentimes the periods in which we were looking at the saturated crevasse systems, we weren't largely focused on what was happening at the calving front until after those sequence of papers between 2013 and 2018, we started to expand the range of research questions that we started asking about them. Like, wow, if there is an impact on the extramarginal field, the extramarginal field is a complicated place by virtue of the fact that we have presence of superglacial lakes. And also we have to contend with the fact that that we have a known relationship between what's happening at the calving front and the observed ice accelerations upstream away from the calving front. So we wanted to try to grapple with that and think about to what degree instantaneous changes and near ice front conditions, which had largely been considered by the work of Joggin and others, that most of the direct influence of calving in terms of accelerating ice occurs within the first 10 or 15 kilometers upstream. But that diffusive effects by the work, recent work by others, that you can get a lower grade propagated influence deeper in the extramarginal field upstream away from the front. But that effect has a certain kind of temporal scale, and its magnitude is muted over time and distance, which means that the influence of the superglacial hydrologic processes that we're looking at in the shear margins and in the extramarginal fields due to superglacial lakes can play a much more pronounced role in modulating whatever the diffusive upstream accentuation of membrane stresses are as a result of terminal dynamics.
Okay. Any other questions? Running past 12.
Sufficiently bored everybody to death. I appreciate you all for your attention and your patience. There's a lot of material to get through it. It's not kind of a standard talk where someone is talking about just one piece of work. We did this work over a long period of time, so I was trying to wrap a bow around it. One day I'd like to write a book, put all this stuff in it.
Yeah, that'd be great. Okay, well, I guess we can stop there. So, thanks again, Derrick.
Thank you, Patrick.
Thanks everyone for coming.
Thank you all. Have a good day.